in the footing design. Then we started designing one rectangular pad footing, in which we already have discussed about the size of the footing, how to calculate size of footing, then how to find out the ultimate bending moment based on the ultimate upward pressure which is acting at the bottom of the footing. And then we also decided the depth of the footing based on the moment resisting capacity of the footing. Okay, up to this we have completed yesterday. Is it clear to everybody, this PDF file?
Yes, ma'am.
Okay. So the next point is check for two-way shear. Now, if you consider this diagram, in this diagram, you can see that a column is resting on a rectangular pad footing. So a load is acting on a column. Normally, we consider an axial load here. We are designing for axial column now, a footing for axial column. So when an axial load is acting here, this load is concentrated at a certain portion on a footing only. And because of that, or if I will consider a plan here, it is concentrated on this particular portion. That is the cross-sectional area of the column. So in this particular region, because of the axial load acting on a column, it gives a punching effect on the rectangular footing. So it is like punching at a specific location on the footing. And because of that, what happens, a certain area surrounding a column, normally that particular area is shown here, this surrounding region, this particular surrounding region gets stressed, and these stresses are most probably or always are the shear stresses. So this particular area gets subjected to punching action because of the excessive shear stresses acting below the column and up to certain or I must say perimeter, along perimeter of the column, and also up to the certain region surrounding the column. Okay. Now, if this punching action or if these shear stresses are higher, the possibility of failure of column may take place, like a fracturing of this entire structure. And how it will fracture? It will form a truncated pyramid. So it will form a truncated pyramid like this. So this particular region will get failed because of the excessive shear stresses acting along the perimeter of the column. This is called as a punching effect or punching shear. And it is also called as a two-way shear because the shear is acting in both these directions. So for this, a check is necessary in the design of footing, and that check is considered as a check for two-way shear. Now for check for two-way shear, we consider a critical section at a distance of d by 2 from the face of the column. Now d means effective depth of the footing, which we have already calculated earlier. We calculated two values, dx and dy. Out of the two, the smaller one is always considered. So dy, if I will go back to these calculations, dx was 490 and dy is 478. So for smaller value, we consider the check for two-way shear. Okay. So the area resisting punching shear, or which is also called as a two-way shear, is calculated by the formula perimeter into D2. Now the area is also denoted by A2 because it is the area corresponding to two-way shear. That's why it is A2. So perimeter multiplied by D2. D2 is nothing but dy here. If I will consider this perimeter, we consider dy by 2 on this side, dy by 2 on this side. So total it will be d plus dy. Similarly, dy by 2 on this side and dy by 2 on this side. So total will be b plus dy. So along this area, there will be a punching action. So this area is calculated as perimeter multiplied by d2. d2 is taken as dy. So perimeter, we can calculate d plus dy. We already know this side plus this side plus this side plus this side. So d plus dy plus b plus dy, both 2 times multiplied by dy. This will give us the area. Okay. So the values are put here. We already calculated the total depth as, the depth of the column is already given as 650. dy we calculated as 478. Width of the column was given as 230. So putting all the values, we are getting the area which resists the two-way shear as 1755.216 into 10 raised to 3 millimeter square. Now this is the actual area we have calculated. Now what is the capacity of the concrete? Now here in this all portion there is a concrete, and the concrete always have a certain shear carrying capacity that we have already learned, or rather when we designed the beams for shear, we already calculated one thing, that is what is the shear carrying capacity of a concrete. So same concept is used here. So what is the capacity of concrete to resist this two-way shear is calculated by using this formula. VUC2, 2 again stands for two-way shear, is equal to tau UC2 into A2. You are familiar with this area, this formula, right? Tau C into area. Tau C, tau U or tau C into BD, that formula we have used for finding VC, okay, or VUC. So the same formula is used here. VUC2 is equal to tau UC2 into A2. A2 is the one which we have calculated already here. Now the tau UC2, this formula is given as Ks into tau C. Now whatever the formula we have used in the design for shear, that we have used for single shear or one-way shear, I must say. Here the shear is two-way shear. So for two-way shear the formula is different, and this formula is given in IS 456. So I will quickly go to IS 456. It is on page number 51, I think, or 58. Let me check. Yes, it is on page number 58, clause number 31.6.3. So permissible shear stress. When shear reinforcement is not provided, we are not providing any separate shear reinforcement for footing. So in that case, the calculated shear stress at critical section shall not exceed Ks into tau C. So Ks is given as 0.5 plus beta C. This value should not be greater than 1. Beta C being the ratio of short side to long side, ratio of the short side to long side of the column or capital. Capital, this particular term is used in case of flats. Okay, so in our case it is column. And tau C is equal to 0.25 under root FCK in limit state method. Okay, so these values we have to use to find out VUC. Okay, so the same formulas are used here. VUC2 is equal to tau UC2 into A2. Tau UC2 is calculated as Ks into tau C. Ks is 0.5 plus beta C, whatever the formula given in the code, 0.5 plus beta C, and this value should be less than 1. Okay, it should not be greater than 1. So the beta C ratio is shorter to longer dimension of the column. So 230 by 650, the values are put, and the value is coming as 0.85. This is the value of Ks, and this value is less than 1. So whatever the value we are getting, that we have to adopt. Suppose in a particular calculation or in particular problem, this Ks value is coming greater than 1, then the value of 1 should be adopted as Ks. Then tau C dash is calculated as 0.25 root FCK. So FCK value was given as 25, M25 grade. So putting the values, we are getting the tau C dash value. Putting the values of Ks and tau C dash, we are getting tau UC2 like this. And by putting this value, we are getting VUC2 like this. So 1.0625 multiplied by this area, we are getting VUC2, and that value is coming as 1864.9 kilonewton. This is the shear carrying capacity of a concrete for a footing, whatever the material we have used for construction of footing. For that, this is the shear carrying capacity of a concrete. Now, what is the actual shear coming on a particular footing, that we have to calculate, and we have to compare it with the shear carrying capacity. Okay, so that shear, that is the punching shear, is calculated as design punching shear, which is called, or which is denoted by VUD2. Okay, VUD2, which is calculated as pressure, upward pressure acting on a column footing multiplied by the shaded area. It means you can, I will go back to this diagram. So in this diagram, actually, what is the punching shear acting? So because of whatever is the load acting from column, the reaction will be developed at the bottom of the footing, and that will be developed uniformly on the bottom of the footing. So this pressure, which is acting uniformly all over the area, that particular area, shaded area only, multiplied by what is the upward pressure acting on a footing, that will give me the design shear or design punching shear. Okay, so VUD2 is WU into shaded area. Now, how to find out shaded area? I know the total area of the footing. So this LF into BF will give me the area of footing minus this area. So this area is D plus DY multiplied by B plus DY. This area, if I subtract, I will get the area of the shaded part multiplied by WU. WU is the total upward pressure, which we have already calculated yesterday, which is coming as 397.35. So AF, LF into BF, we are getting AF as 4.53. And this is the area of the unshaded portion. Okay. So after doing the calculation, we are getting this VUD2, that is a design punching shear, as 1482.6 kilonewton, which is compared with VUC2, which is less than VUC2. So this is safe. It means our footing is safe under punching shear or two-way shear. If not, suppose this force is coming greater than our VUC2. So in that case, what is required? What correction we need to do? We need to increase this A2. Now, how to increase this A2? For increasing the area, we have to increase D or B. D or B may not get increased because these are the size of the column. So what we have to increase? We have to increase the depth of the footing. Okay. So if this punching shear is not satisfied with this criteria, you have to increase the depth of the footing. That is the solution for getting this particular check. Okay. Is it clear, everybody? Concept of punching shear. Guys, am I audible?
Yes, ma'am.
So is it clear to everybody?
Yes, ma'am.
Okay. Now the next step is calculation of area of the steel. Now, as I explained yesterday, the area of the steel is provided to resist the movements acting on the footing. Now these movements MUX and MUY, which are acting along both or about both the axes, for those we have to calculate the area of the steel. Now for MUX, now how this moment is acting? It is a moment acting about x-axis. So I will go back to the diagram now. If we consider this cross section or the top view of the footing, this is the x-axis and this is the y-axis. X-axis is placed or is considered according to the axis of the column. Okay, now how to consider these axes for column? X-axis is always perpendicular to the depth of the column. Keep this in mind because this is very important. X-axis is considered always perpendicular to the depth of the column or larger dimension of the column. So this is the x-axis and this is the y-axis. The moment is acting about x-axis. So the moment is acting in this fashion. So the moment is acting here and here across this footing about x-axis. So this moment is registered by the steel provided in this direction. So this direction is the steel direction which is perpendicular to x-axis. Okay. So to resist the movement about x-axis, the steel or reinforcement is provided perpendicular to x-axis. Normally, we have a habit about x-axis or along x-axis means we provide the steel along x-axis. So this is not the case in case of footing. Okay, movement is about x-axis, so reinforcement is placed perpendicular to x-axis. Similarly, when a moment is acting about y-axis, the reinforcement is placed perpendicular to the y-axis. So whatever is the movement, this movement is resisted by the reinforcement provided in this direction. Okay, so that's why it is written, clearly written here, that for MUX, that is the AST, whatever we are providing, it is provided perpendicular to the x-axis. Now the same formula which we have used for slabs or for beams, we have used this formula for finding the area of the steel. Same is to be used here because actually footings are nothing but slabs only. Okay, so 0.5 FCK upon Fy, this formula, you are well aware of this formula. MUX value, whatever we have calculated, that is to be considered here. B, width, is the width of the footing now, that is BF. Okay, B1 is nothing but BF here, and DX. Now, as we are considering the movement about x-axis, we have to consider the depth along x-axis. Okay, so or the depth to resist this MUX, whatever we have calculated, or the depth which we have calculated based on MUX, that is to be used here. Okay, so this dx value is considered in the calculation. Okay, so all these values are put and we get the AST value here. We have to compare this with the minimum AST. Now minimum AST formula is the same which we have used for design of slabs, right? Slabs or beams? This formula?
Beams.
So this formula is for beam, minimum AST for beam. So that formula is to be used over here. So AST should come greater than the minimum AST. Now 0.85 BD, again B should be the width of the footing, and DX is to be used here divided by FY. So this value is coming as 1612.31, whereas the minimum area is coming as 1936. So we need to provide the minimum value here. Okay. Now again, as I discussed yesterday, to decide the AST, normally we decide the diameter of the bars here. The same way what we have done in case of column. We decide the diameter of the bars and then we calculate the number of bars based on the diameter, or we have to consider this as per the design of the beams, not columns. In design of beam, what we have considered, we assume the diameter of the bar and then total area divided by area of the single bar. That gives us the number of bars. In column, we did exactly opposite. We consider number of bars and then we calculate the diameter required. So, okay, this is done as per the beams. Okay, so we assume the diameter 12 mm and then we calculate the number of bars required. Okay, so accordingly, the bars are coming, number of bars are coming as 18 numbers, 12 mm diameter bars. So what is the actual AST provided? That is calculated here, area of a single bar multiplied by number of bars. So this is coming as 2035 and the required is 1936. So this is satisfactory. Now, one more check is here, check for development length. Okay, the one which we used for the slab. So if you consider the design of footing, it is a combination of the beam and design of slab. Whatever the steps we are following for beam and for slab, the combination of both these is used for design of footing. That's why it is little bit lengthy. Now the check for development, this formula we already know, LD, we already discussed that 0.87 Fy upon 4 tau BD into phi. This formula gives us the required length or the required development length for the reinforcement. Okay, so by making use of this formula, 0.87 Fy upon tau BD is calculated as the same way whatever we have done for design for slabs. Okay, so those values are calculated here and the value is coming as 483.6. This is the required development length. What is the available development length? Development length is actually the length of the projection which we are providing from the facing of the column. Okay, so Cx or Cy. So Cx or Cy both we have provided same here, equal here. So it is 850 mm. So the available development length is 850 mm and the required is 483. So this is also satisfied. This check is also satisfied. If not, if this check is not getting satisfied, then Cx is to be increased. Okay. So this is about development check along x-axis. Now we have calculated the area of the steel and the development length for x direction. Similarly for y direction, that is the for the MUY, for to resist the MUY. Now MUY, this based on this moment, whatever the area of the steel we calculate, it is provided perpendicular to the y direction. Okay, it is to be provided perpendicular to the y direction. So again, the same formula is used here. Here MUY value is to be used. B instead of B, now for X calculation we have used BF value. Here we have to use LF value, length of the footing. Okay, and DY. Okay, because it is MUY, so the DY value is to be used. So putting all these values, the area is coming as 2015.56. Comparing with the minimum value, now here the minimum value is to be again considered for LF, LF and DY. So those values are, this value is coming as 2300 and the AST is coming as 20. So again we have to provide the minimum value. Again, whatever the bar diameter we have used in X direction, same is to be used for Y direction. Number of bars we need to calculate accordingly. So number of bars are coming as 21. So provide 21 numbers, 12 diameter bars, 12 diameter bar. So provided AST is calculated again here. Okay. Now in this case, again, if you go back to this calculation, the calculation will remain same, development length, because it is 483 and the CY value is also 850. So again, for Y direction, there is no need to show the development length. It is the same as whatever we are getting perpendicular to the X axis or along the Y direction. Okay, is it clear? Area of the steel calculation.
Yes,
Okay.
ma'am.
Now the next step is check for one-way shear. We have checked for two-way shear. Similarly, we have to check for one-way shear. Now for one-way shear, again, a critical section is considered at a distance D from the face of the column. Okay, so if I will consider the diagram here for this footing and column consideration, or this is the plan of the footing and column. For one-way shear, the critical section is considered at a distance D from the face of the column. Now here we do not consider the minimum value. We consider whatever is the D value along X and along Y direction, or dx and dy. For those we calculate the one-way shear or do the calculation. Okay, so along x-axis, that is along this axis, the depth is dy. So for this particular area, on this particular area, or at a distance dy from face of column, this particular line is the critical section. So along this critical section, whatever is the shear that we have to calculate. Okay, so area resisting the one-way shear is calculated as df into bf. This is the total area. The entire area of the footing is subjected to one-way shear. So df into bf, that value is calculated as A1x. Okay, then percentage steel based on that is calculated, which is coming as 0.19%. Now the shear force resisted by concrete, here the formula is to be used same as that of whatever we have used for design of shear for beams. Okay, so tau C VU C1x is equal to tau U C1x into A1x. Okay, 1 is again because of the one-way shear. Okay, now here the tau U C value is calculated against the percentage of steel. If you remember table 19 or table 20, I don't remember the table number now, but table 19 or 20, out of these, one table gives us the tau C value. Okay, so this tau C value is calculated based on the percentage steel and FCK value. So based on that, the tau C value is calculated as 0.318, and then we calculate this VUC as tau C into A1x. So this area multiplied by this tau C, it is giving us the total shear force resisted by the concrete. So this is again a shear capacity of a concrete in one-way shear. Now we have to find out the design shear force. So the concept is same. Whatever is the uniform pressure acting on the footing multiplied by the shaded area. Now here the shaded area is different. This is the shaded area only. Okay, so either on this side or this side, whatever is the side, this will be the shaded area. Now for finding the VU D1x, the shaded area is BF into CX minus TX. So this side along x-axis we are calculating. So along along x-axis, along this axis, the area is this one. Okay, so this is our x-axis. Along x-axis, this is the area. So this area, what is that? This is BF into this distance. Now how to find out this? It will be total distance. Where is the formula? CX minus TX. This is the total distance. From the face of the column up to this edge, this total distance is CX minus this DX. It will give me this length multiplied by BF. It will give me this entire area. Okay, so along x-axis, this is the strip, okay, on which the one-way shear is acting. This area is to be considered. So that area is calculated like this, and the value of VUD, that is the design one-way shear, is coming as 276 kilonewton, which is coming less than the shear capacity of the concrete under one way shear. So this is again safe. Now suppose this check is also not satisfied. What to do? We have to increase this VUC1 value. So to increase the VUC1 value, we have to increase the dimensions of the footing. Now in case of two-way shear, we have to increase the depth of the footing. Whereas to get the one-way shear, if the check is not satisfied, then we have to increase the lateral dimension of the footing. Okay. Now we have calculated the one-way shear along x-axis. Similarly, along y-axis is calculated. So A1y, this value is calculated as dF into LF. Okay. Then percentage steel is calculated. Let me check what is dF and LF. Okay. Okay, dF into LF. Fine. Then shear resisted by the concrete. This value is calculated. Now percentage steel is different, so your tau UC value will be different, and area is also coming different. So this value VUC1 is calculated like this, and then again we have to calculate the design one-way shear by using the same concept. So here along the y-axis, this will be the straight. So we have to find out area of this shaded portion. Okay, so that area is considered over here, and this check is also getting satisfied. So the design of footing is safe in this case also. Okay, is it clear, everybody? The check for one-way shear. Guys?
Yes, ma'am.
Yes, ma'am.
Then the last check is check for bearing pressure. Now check for bearing pressure, to find out that the bearing pressure is calculated by this. It is the force divided by the area of the column, bearing pressure. Now load coming on a column is 1800. It is the factored load, taken as factored load, divided by area, cross-sectional area of the column is B into D. That value is coming as 12.04 kilonewton. And this bearing pressure should be less than the permissible bearing pressure. Now why it is bearing pressure? Again, see, the load is getting transferred from column to the footing. So because of the axial load acting from column, there will be a pressure acting on this particular region, that is exactly below the cross-sectional area of the column. The part of the footing will be stressed more. Okay, so that bearing pressure is calculated here. So that stress is coming as 12 Newton per mm square. It should be less than this formula. Now this formula is given in again IS 456 on page number, I think 65. Let me check. 63, 65. Yes, this is transfer of load at the base of column. The compressive stress in concrete at the base of a column or pedestal shall be considered as being transferred by bearing to the top of the supporting pedestal or footing. The bearing pressure on the loaded area shall not exceed the permissible bearing stress in direct compression multiplied by bearing stress in direct compression multiplied by a value equal to under root A1 by A2, and this value should not be greater than 2. What is A1? A1 is the supporting area for bearing of footing, which is sloped or stepped footing, may be taken as the area of lower base of the largest frustum of a pyramid. In short, A1 is the area of the footing. Okay, in case of slope footing or step footing, what should be done? It is given here, but we are considering only the design of rectangular pad footing for your syllabus. Okay, so we will consider here the rectangular pad footing area as A1, and A2 is the loaded area at the column base. That is again the cross-sectional area of the column. Okay, now for working stress method of the design, the permissible bearing stress on full area of concrete shall be taken as 0.25. For limit state method, the design permissible bearing stress shall be 0.45 FCT. So what is the criteria here? The bearing pressure on the loaded area shall not exceed the permissible bearing stress in direct compression multiplied by this. So for limit state, the permissible bearing stress is 0.45 CK multiplied by under root A1 by A2. This is the limiting value. So accordingly, this formula is taken here. Okay, so permissible bearing pressure is 0.45 FCK under root A1 by A2. A1 by A2, this ratio should not be greater than 2. So A1 is actually the area of the footing or this criteria. I must read it full now. Okay. May be taken as the area of the lower base of the largest frustum of pyramid or cone contained wholly within the footing and having for its upper base the area actually loaded and having side slope of 1 vertical to 2 horizontal. So this is having a slope of 1 vertical to 2 horizontal. Based on that, the criteria is coming like this. Okay, so 1 vertical, 2 horizontal. Based on that, the B plus 2 DF and D plus 2 DF, that calculation is calculated here. So the first one is the multiplication, or sorry, the area of the footing, LF into BF, that is coming here. And second is this criteria. So as per this, B is the 0.23, that is the dimension of the column, width of the column, plus 2 times the DF. D is 0.65 plus 2 times the DF. That value is coming as 2.33. Out of these two, least value is to be adopted as A1. Okay. So A1 upon A2, this value, A2 is the cross-sectional area of the column, which is calculated here. A1 upon A2 under root, this value should be greater than, sorry, should not be greater than 2. So here the value is coming as 3.94. So we have to add up the value as 2 only. Okay. So putting these values here, we can find out the permissible bearing pressure, which is coming as 22.5. Okay. So permissible bearing pressure, after putting all these value here, we are getting 22.5, and this should be greater than the bearing pressure, whatever is the bearing pressure. Okay, so this is the actual bearing pressure coming from the column, and this is the permissible one. So whatever is the allowed, this is the limit. The bearing pressure should not be more than this value. Which value? This means 22.5. Okay, and actual acting is 12. So the design is safe here. Okay, so this is for bearing shear check, bearing pressure check. This is a diagram which is expected at the end. A simple diagram, a column, from a column, a reinforcement is coming and it is placed here. And this is the reinforcement for which we have designed it. Okay. So along the y direction or perpendicular to the x-axis, this reinforcement is placed at the bottom, which was coming as 18 number of 12 mm bar diameter. So these are placed over here, this horizontal line. And above that, the total 21 of 12 mm diameter bars are placed in this fashion. Okay, so this diagram is expected. This diagram is still incomplete, is not properly drawn. The dimensions of the footing, the depth of footing, everything should get appeared in this particular diagram. Okay, is it clear? Design of footing, guys?
Yes, ma'am.
Okay. Now, this is the design for footing for axially loaded column. The design steps are lengthy one, but easy to understand, not so difficult. But the design for axially loaded column, these design steps we have discussed. Similarly, for uniaxially loaded column, that is the column with axial load plus moment, that also to be considered, because in your term work, we have such columns now which carries the moment also along with the axial force. So for that, you have to design the footing which has to carry the axial load along with the moment. Okay. For that, we have to consider the another problem. So I will start that problem also, because we have almost 20 minutes more. So this is a problem statement which is considered. Initial 2-3 steps we will finish today, and the remaining part we will see in the tomorrow's lecture. So I'm again considering a PDF file here, a solved example. The problem statement is here. Design an isolated footing for column 300 by 450 mm subjected to working load of 600 kilonewton along with working moment of 75 kilonewton meter about an axis bisecting the depth. Now, just now I have explained that the axis is considered, x-axis is considered as the axis which is perpendicular to the depth. So this is the moment about that axis. That is, this is the moment about x-axis. Okay. So this is actually MUX given in the problem. Now take safe bearing capacity of a soil equal to 225 kilonewton per meter square and use M20 and Fe415 materials. So this is the given data. Now the first step is to decide the size of the footing. Now if you remember the same step what we discussed in yesterday's lecture, the size of the footing we calculated based on the pressure which is acting on the footing, right? So based on what is the load and then what is the self-bearing capacity, based on that we calculated the pressure and what is the area required to calculate that, to bear that pressure, that we have calculated. The same thing we cannot do here, because in that calculation, in yesterday's calculation, we were having a uniform pressure below the footing, okay, because there was only axial load acting on a column. Now in case of the column which is carrying moment also along with axial load, the pressure acting at the bottom of the footing is not uniform. It always vary non-uniformly, okay, or there is a variation in the stresses developed below the bottom of the footing, okay. And as the pressure is not uniform, we cannot consider directly the projections and we cannot calculate the area of the footing directly, because in this case the projections are not equal. Why not equal? Because the column, when it carries axial load and moment, it is always, the system is always replaced by a eccentric load, right? It means we consider that the load is acting at a certain eccentricity on the column. We replace the entire moment and the axial load in this fashion, that is the load is acting at a certain eccentricity. Now obviously the side on which the load is acting, that particular portion will get more compressed, and hence the pressure below that footing will be more, and therefore the dimension of the footing required on that side will be more, okay. Suppose this is our footing, and my load is acting somewhere here. So on this side my footing is subjected to more compressive force, and because of that the pressure acting at the bottom of the footing is also not uniform throughout the length of the footing, but it is more on this side, and hence this projection required is more as compared to this projection, okay, along the direction which is perpendicular to the x-axis. The product projection required will be more as compared to the projection in a perpendicular direction, okay. So because of this, we always calculate dimensions of the footing based on what is the eccentricity of the load acting on the footing. And when the eccentricity is calculated, I think you already have considered a middle third rule. You have already learned the middle third rule in SOM. So according to that, if we don't want any tension to be developed at the base, the eccentricity should be here. The eccentricity should be less than the longer direction divided by 6 of the plate or the footing, okay. So eccentricity should be less than or equal to LF by 6 if we don't want any tension. It means at the bottom of the footing, if we want a compression only, no tension. If there will be development of tension, that particular part of the footing normally do not have a contact with soil. It remains in uplifted position. Okay, so that eccentricity is practically checked at every corner, and whether all the corners are touching to they remain touching to the soil or not, that is checked, okay. And that care is we need to take that care, that eccentricity should not get exceeded by the value LF by 6, okay. So for no tension condition, E should be less than LF by 6. So LF is considered or adopted according to this condition, okay. So LF should be greater than or equal to 6 times the eccentricity. So here in our case, we have to first calculate the eccentricity, which is calculated as mu upon pu. Mu is given as 75, right? So this value is working moment, so it should be converted first to the design moment. So by applying the partial safety factor, the value is converted into design moment. Similarly, the working load is given as 600, so it is converted into design factor or factored load, which is coming as 900. 600 multiplied by 1.5. Okay, so these factored values we have to consider here to calculate eccentricity. So E is calculated as 125 mm. Okay, So
Ma'am?
6 times, yes.
Ma'am, yesterday we considered the partial safety factor as 1 because of limit state of serviceability. So in this, what is the limit state that we are considering?
Limit state is considered here because we are calculating or deciding the dimension based on the eccentricity. Now, eccentricity means we are actually dealing with the strength, limit state of strength, and hence we have to
Okay.
consider the partial safety factor according to that. We are not considering
Okay, ma'am.
here the deformation or settlement criteria here for deciding the dimension. Okay.
Okay, ma'am. Thank
For
you.
this, for E calculation, I'm talking about only E calculation. If you consider the area required calculation, again, we are moving to the same condition here. Are you getting here?
Yes, ma'am.
Eccentricity is calculated based on factor value. So from that, the LF is coming as 6 into 125, which is 750. So my length of the footing must be greater than 750 mm or at least equal to 750 mm. Okay, this is the condition now, what I have got. Now again, while calculating the area, I will make use of the same formula based on the settlement criteria as we have done in the yesterday's problem. So which is load coming from the column divided by the safe bearing capacity. So that load is increased by 10% to add the self weight of the footing also. So it is 1.1 into 600. Now again, this load is to be considered as per the as a working load because this criteria is coming under the limit state of serviceability. Here we are considering the area required based on the settlement. Settlement is the deformation. Based on the deformation or considering the probable deformation, the area required is calculated. But here when we calculate the length requirement, it is considered based on eccentricity, and eccentricity is having a connection or it is related with the strength of the column. So the values are considered as a factor. Okay. So this area is coming as 2.93 meters square. Now we have LF is 750. That is the criteria. That is the condition. So 2.93 is the required area. So how to decide now length and width? Because Cx or Cy, these values are not known to us. We cannot consider here because we don't know how the pressure is varying. Okay, what is the intensity of a pressure right now? So what is done normally 2.93, if I will assume a square footing, I will simply take a square root of this 2.93. Okay, so square root of 2.93 is coming somewhat 1.71. So I can consider the width in a range of 1.71 and the length also according to the required one. Okay, so now the required one is actually minimum is 750, and I already know that there is a moment. So one dimension or in one dimension, I can provide either a square footing or a rectangular footing. So as I yesterday discussed, it is given that the column is of rectangular cross section. So obviously I have to consider a rectangular dimension of the footing. So what I did, I have taken a square root of this 2.93 and the square root is coming as 1.71. So I will approximately considering the BF as 1.75, and then obviously the required area is 2 and we have to provide the higher area. So I have simply increased this dimension by approximately 1 meter or 1.5 meter to get the length of the footing. Okay, so this is how I have considered the dimension of the footing. So by considering this value first, BF, this is shown in different fashion. Initially you can assume the length also, which is 2.5 meter, and then BF is calculated like this. But what value is to be assumed here initially, we don't get any idea. So this is the another way. So simply take a square root and whatever the value is coming, provide it as a BF value. It is rounded off to 1.75, and for that value find out LF. Okay, this becomes a little bit logical assumption. Okay, it gives some logic for your assumed value. So the LF provided is 2.5 meter and BF is 1.75. So the provided area is coming as 4.375 meters. Okay, this is the area of the footing. Now the next step is calculation of ultimate bending moment. Now this step is little bit lengthy, or you need to understand the concept here. Now the bending moment in the earlier case we calculated by using the normal formula. No, sorry, not normal formula. By using the uniform pressure, by considering the uniform pressure acting below the footing or acting at the base of the footing. Okay, so we calculated what is the uniform pressure acting at the base of the footing, and accordingly we calculated the bending moment. Okay, that uniform moment is acting on the Cx value and Cy value, and accordingly we calculated the moment. Now this is not the way for calculating the ultimate bending moment here in this case, because this footing is subjected to combined action of axial load and moment. So we need to consider a combined pressure, and that combined pressure is obviously, as because of the presence of moment, it is not uniform. Okay, so that value is calculated by using this formula. This formula you have already learned in SOM, right? It is giving us the combined stress, the stress due to axial force and stress due to moment. Okay, so P upon A plus M by Z. This formula you have already learned in SOM. So this, by making use of this formula, we calculate what is the maximum ultimate upward pressure acting on a footing. Okay. The maximum upward pressure calculated in the earlier yesterday's problem is different. It is simply load upon area. Now here we cannot consider load upon area, like, which is the first part of this formula. We have to consider the effect of moment also. So this is giving us, the PU max is giving us the maximum ultimate upward pressure. And as the pressure is not uniform, it means it will be maximum at one edge and minimum at the another edge. So PU minimum also we need to calculate, which is PU upon AF minus MU upon ZF. Okay. So P is the factored load acting on a column, which is 900, divided by area of the footing, which we have calculated as 4.3750, plus moment acting on a column is 112.50, divided by ZF is nothing but a section modulus. Okay, so for rectangular section, the section modulus formula is 1 by 6 BD square. Okay, so here the rectangular section is nothing but our footing. So it is 1/6. The B is the BF, the width of the footing, and D is the depth, that is the length of the footing, LF square. So 1/6 BF into LF square, that formula is used here. Okay, to find out the section modulus. So by calculation, we are getting the value as 267.42. This is the maximum upward pressure. It should be less than 1.5 safe bearing capacity. This we discussed yesterday. So this is coming as 337 and this value is 267. So this is safe. If not, what to do? If it is coming greater than the soil bearing capacity, what to do? I need to increase the area, or I need to decrease the area. What should be done?
Increase the area.
So if I will increase the area, this value will be again, this value will be lesser. Okay, so this value will be ultimately lesser. So I have to increase the area of the footing if this check is not satisfied. The next is minimum calculation of minimum ultimate upward pressure, as we discussed. So this is a PU minimum, this value, and the minimum value should be more than 0. Okay. So this is the minimum and maximum. These are the minimum and maximum pressure intensities below the footing, which are shown here in this diagram. Okay. So this is the footing. This is the minimum pressure 144, and this is the maximum pressure 267.42 on 1H. Now, based on this, now we can find out what should be the projection of the footing beyond the face of the column. Okay, now these are calculated like this. We have already provided LF and BF. So LF minus D. I don't have a cross-sectional view here. So this is the LF value. This is the LF value. LF minus D, it will by 2, it will give me the CX projection. And similarly, BF minus this B value by 2, it will give me the CY projection. So the same is calculated over here. LF minus D by 2. So the value is coming as 1.2. And then projection beyond projection of the footing beyond the face of the column perpendicular to the y-axis is calculated like this: bf minus b upon 2. So these are the projections, and the projections are coming different here, and this is because of the differential pressure acting on the non-uniform pressure acting on the bottom of the footing. Okay, so in this fashion we calculated the projections. Now ultimate bending moment, again we calculate at the face of the column. Okay, see, this is the face of the column, so this is the critical section at which we have to calculate the moment. Okay, in yesterday's problem also we calculated the ultimate moment at this location by considering the load acting on this area. Now here the load or the pressure acting on this particular region is not uniform, it is varying. So we have to consider whatever is the pressure, non-uniform pressure acting on this particular location, what is the actual intensity of pressure acting at this particular face, and based on that we have to calculate what will be the mu-x value and mu-y value. Okay, so these calculations are little bit complicated to understand. I think we will consider these details in the tomorrow's lecture because we have already crossed 12:15. And truly speaking, we require a very calm mind to understand these calculations because we require a 3D visualization to understand how the pressure intensities are acting below the footing. Okay, so this part we will see in tomorrow's lecture. The remaining part rather we will complete in the tomorrow's lecture. I hope whatever I have explained you right now is clear to everybody. These PDF files I'm going to upload on BOLP. Attendance link I think I have not given, so let me get the link first and I will give you that attendance link here. Yes, the attendance link is given in the chat box. All are requested to give the attendance through the link. Any doubt?